So now we're going to talk about projectiles. Now, projectiles all follow the same path. That path is called a parabola, a name you may remember from math. But we see this kind of motion, this projectile motion, almost everywhere that we look. So in sports, we see this kind of motion everywhere. A basketball is a projectile. A pitched baseball is also a projectile. But so is the thrown ball. The thrown ball is going to be a projectile too. All right, so in sports, again, these are everywhere. Here's a long jumper. Humans can be projectiles. So he's going to hit this board, and you're going to see he takes off, and basically gravity's controlling his flight. So there he becomes a projectile, and you can see the parabolic shape to his motion there. A drinking fountain or a fire hydrant can be one. And here's another one of humans. Boop, away he goes. Here's a guy in a motorcycle. He and his motorcycle are projectiles, at least until he pulls the cord on his parachute. So again, you see this kind of projectile motion all over the place. Anything that's moving through the air that has only gravity working on it could be considered a projectile.
Getting up to about 145 feet in the air before he pulls his chute.
What exactly is a projectile? Well, a basic definition for a projectile is it's going to be an object that moves through the air with only gravity acting on it. On it. Okay. So if you read that definition, that essentially sounds just like the definition of what free fall is. If I take an object and I drop it, we usually assume that if it's in free fall acceleration, it's in free fall motion, that only gravity is acting on that object. And you'd be right. I mean, this part of the definition of a projectile is essentially just free fall. It's free fall that we covered in the last chapter. There is one difference. And what we would add to this is it's an object that moves through the air with only gravity acting on it, but it has with, so we'll say with, a horizontal velocity. So basically, apart from the horizontal velocity, it is just free fall. A projectile is essentially vertically moving, just like it's in free fall. The only difference between free fall and a projectile is the projectile has a forward motion. It's moving forward while it's falling. Now, if you do that, if you have that kind of motion, so let's just say that you're diving off of a cliff, you're at the river or something, you're diving off a cliff and you're going to land in the water. What we would basically say is the moment your feet leave the ground, the only real force that's acting on you is gravity, which is pulling you straight down. Okay, gravity is going to be pulling you down, but there's no force horizontally acting on you at all. All right, you're essentially in free fall from that point of view. It's just that you're also moving forward. You're moving forward at the same time. All right, so that's what projectile motion is. If you follow that path, what you'll find is every single time you look at a projectile, if only gravity is acting on it, you're going to follow a particular path, and that is the path of a parabola. So we will say that you will follow a parabolic path. All right? You may have heard this term from math before, but a parabola basically is going to look like so. Okay? I can change things a little bit. I can go steeper. But it's always going to follow the path of a parabola. So what is it that produces this parabolic path? Why do projectiles always move with that shape? Well, if we imagine a ball rolling off of a table, and if we think about the motion of that ball, we can kind of get some ideas about what must be happening. What you'll notice is if I were to take pictures every split second, but the same amount of time, so maybe it's a tenth of a second, a tenth of a second, a tenth of a second, what you'll notice is that this ball is going to have a forward velocity. All right, it's going to have a forward velocity the moment it leaves the table. But what would you say about its vertical velocity at that moment? The moment it leaves the table. Well, because it was rolling completely horizontally across the table, it doesn't have any vertical velocity when you hit the edge. But as soon as you go off the edge, a new force starts to act on you. It's gravity. Gravity starts to pull you down. And gravity produces an acceleration. Remember what that means. It's a change in velocity, right? So my vertical velocity at that moment that it leaves the table, my vertical velocity is 0. But after a tenth of a second, I'm still going to have that forward velocity. All right? It's the exact same one that we started with. But now I'm going to start to get a vertical velocity. And that vertical velocity, again, is due to gravity. Now, if I were to connect these head to tail, so if I took this guy right here, and instead of having this vertical velocity connected to the tail here, if we took that off, I'll just get rid of that a little bit, but we slid it over here, I could then connect the very beginning to the very end, just like we did when we were talking about vectors the other day. And what I would see is my path, when I combine those two, kind of goes in this direction, the direction that it is falling. Now, if you go another split second, you're going to still have forward motion, but if gravity is still acting, what's going to happen to this vertical one? Well, this vertical vector is going to get longer now because gravity's had more time to work on it, and you're going to increase that velocity in the vertical direction. And so if I were to slide this over here, I'd have a path that kind of went like that. If I go another split second, you're going to see the horizontal kind of goes off in that direction, but now the vertical is going to be even longer. Again, gravity continues to work. And so we, in essence, went from having no velocity. I'm going to kind of get rid of some of this and redraw my line. In essence, we went from having no gravity here, a little bit of velocity. Well, gravity's still acting, but it's not pulling the ball down. You're going to get a little bit of vertical velocity here. You're going to get a little bit more here and a little bit more there. And every split second that you continue to fall, this vertical velocity is going to get longer and longer and longer. So your motion seems to be more vertical when you get a decent time pass. You're going to have more vertical velocity than you do horizontal. Well, if you look at the way that a parabola works, again, if I'm on that cliff and I launch a ball off, it's going to kind of take a path that looks like that. So in the beginning, you've got a lot of the horizontal is pretty big compared to the vertical. But when you get towards the end, the vertical velocity is way bigger than the horizontal is. Now, there's something else I want you to pay attention to. Look at the horizontal arrows. What do you notice about the horizontal arrows on each of those pictures of the ball that we put up there? What do you notice about the horizontal arrows? Well, if you pay fairly close attention to them, I tried to get them the right length, but they should all be the same length. All right, now what would this mean? This would mean that there isn't any force acting horizontally. There's nothing to speed up or slow down this horizontal velocity. That takes a force. So we're saying there is no force that is changing this velocity. However, gravity is changing this vertical velocity. So again, a projectile, only gravity is acting. That's why this vertical velocity changes, but the horizontal one does not, because gravity doesn't act sideways. It acts vertically up and down. So now we're going to go to the bleachers, and we're going to throw a projectile off of the top of the bleachers. We want to look at the velocities, the horizontal and the vertical velocities, and then we're going to look at them even closer in slow motion. 3, 2, 1, launch. So now what we're going to do is we're going to break this movement of the projectile into equal size segments. And for each segment, we're going to show where the ball is at, and then we can use the position of the ball to help us figure out what kind of motion we're looking at here, whether it's constant or whether it's accelerated, for both horizontal and vertical. All right, now that we have points where the ball was located at different times, remember that each of these times, the top dot here is at time 0, the second one is at time 0.2, next is 0.4, 0.6, 0.8, and then finally 1 second. So these dots were at 0.2 second intervals, every single one of them. So now what we want to do is we want to think about the horizontal motion of that projectile as it was moving through the air. So we're going to take each of these dots and we're going to make a copy of them, and we're going to run them up to the very top of the screen. All right? The reason for doing this is I want to take a look at how far apart all of these dots are when we think about the way they moved horizontally. So if we look at these dots now, you guys, the ones that are along the top of the screen, remember that when we talk about motion, we really only have two types. You either have constant motion, where the object moves the same distance every certain unit of time, or you have accelerated motion, where the velocity changes over time. Now, if you look at how these dots are arranged horizontally, that horizontal line on the top, what do you notice about the space in between the dots? Is it changing wildly as it went from the top of the bleachers to the ground? Do you see a big change every 0.2 seconds? Or does it look like pretty much the same change every 2 seconds? If I'm looking at this, I see that the gap in between those dots along the top of the screen looks like it's the same distance pretty much every unit of 0.2 seconds. It doesn't change. And if you cover the same distance during the same amount of time, that must mean that your speed doesn't change. So this is proof, experimental proof, that the horizontal velocity of a projectile is constant. It doesn't change. All right? So next we're going to look at the vertical velocity. So now we want to think about the vertical velocity of this projectile. So just like we did before, we're going to go ahead and instead of taking that path that the projectile took and running copies of the dots to the side, we're going to use lines this time. So we're going to run some lines from the dot itself over to the left of the screen. And again, what we're going to want to do here is we're going to want to pay attention to the distance in between each of these lines, because it's going to tell us something about the velocity, vertically that is. So let's look at these vertical lines. What I want you to notice is the spacing in between each of these lines. Remember that those dots that make up the motion of the projectile, that parabola that we see there, each one of those was recorded 0.2 seconds apart from each other. So what you can see is that the top line here, the distance between where we started and then that first 0.2 second interval, that tennis ball, our projectile, moved hardly at all during that first 0.2 seconds. During the second 0.2, so to get to the to the third dot from the top, it moved a little bit more. And to get to 0.6 seconds, it moved more still. So in between each of these 0.2 second intervals, would you say that motion is constant? Remember what we saw with the horizontal. The horizontal was every one of the distances in between each of those 0.2 second intervals, they were exactly the same because the horizontal velocity was constant. Can you say that the vertical velocity is constant? If I look at these gaps, I can see that clearly it's not. This velocity as you're moving towards the ground, when I think vertically, looking at the red lines, I can see that that spacing in between each of those lines gets bigger and bigger and bigger, meaning that ball is accelerating vertically. Vertically, it is moving faster and faster and faster. Now, if we understand what a projectile is, this makes total sense. Remember, there's only one force acting on a projectile, and that's gravity. And gravity doesn't act horizontally ever. That's why that horizontal velocity did not change. The vertical velocity, however, it has gravity acting on it. And so that force of gravity is going to cause a change in velocity that we know as acceleration. That's why those lines are not the same distance apart. So let's review the velocities that we see with projectiles. What happens with the horizontal velocity of a projectile? Well, as we saw in the experiment where we threw the ball off the bleachers, the horizontal velocity, the distance that that ball moved horizontally, stayed the same throughout the whole time. And so what I would say about horizontal velocity is that it is constant. All right? There is no change in velocity that occurs horizontally. All right? Now, the reason for this should make total sense. Remember that just like free fall, we're ignoring air resistance. And air resistance would be the only thing that could provide any force as that ball moves horizontally. And without air resistance then, the velocity should stay the same. Now, what that means is, if you ever want to know anything about the horizontal velocity of a projectile, there is only one formula that you will ever have to use. And that is the basic average velocity formula that says velocity equals displacement over time. That is the only formula that you will ever have to use when you talk about the horizontal velocity of a projectile. Okay? Now, the vertical velocity is a little more complicated because what we saw in the experiment with the ball is that that velocity was not constant. The velocity vertically is accelerating. So what we could say is that this is accelerated motion. So if I think about what kind of formulas I might use for vertical velocity, remember, being accelerated motion, you're going to use all of those 5 variable formulas that we went over in the previous section. All right? So, and I'm really talking mainly here with AP Physics. Regular physics, you guys, we didn't really go into those formulas too much, but AP, you guys know the formulas I'm talking about. You would use those with the vertical. Now you might say, well, wait a minute, I got to use 2 formulas at once? No. You solve the vertical motion and you can solve the horizontal motion as 2 different things. So we're talking 2-dimensional motion here. It gets easier if you don't try to lump everything in at once. So I'll go back up here. What produces the parabola's path? That path that every projectile is going to take? Well, it's simply the combination of these 2. So what I would say here is, what produces parabola's path? It's basically the combination of the horizontal velocity and the vertical velocity. Vertical velocities. Okay? So this essentially, you guys, is how projectiles work. This is how projectiles form the path that they take. It is the combination of that horizontal constant velocity together with the vertical accelerated downward due to gravity, that velocity. The combination of those two is going to give you a parabola. Okay? And I will also tell you, the horizontal velocity has absolutely nothing to do with the vertical. You can treat those as two completely separate velocities, and then when you need to, you can recombine them if you have that need based upon the problem that you're looking at. Okay? So this is the basics, you guys, of projectiles. We're going to do some practice with this and look at a lot of examples, but this is the basic idea. All right, so I hope you learned a little bit today. Don't forget, the horizontal velocity is constant and the vertical is accelerated. That's going to be something that you see over and over again. Again, remember it, and I will see you next time.